In 7, we've got 2 points, P and Q, that are given in rectangular coordinates. P having rectangular coordinates 2, 1, 5, and Q having rectangular coordinates 7, -2, 4. And the directions say, write the vector, parametric, and symmetric equations of the lines that are of the line described by these 2 points. These are 2 points in space that determine a line because they're not the same point. We want to describe this line with equations in different forms. 3 equations: a vector equation, a system of parametric equations, and what are called symmetric equations. Let's attempt a drawing. I typically like doing it with the positive x-axis coming out toward you. Positive y-axis to the right, positive z-axis going upward. For P, x is 2, y is 1, z is 5. So when I try to draw that, maybe make a little box here. Oh, it happens to look like it's on the z-axis, but it's in front of the z-axis. It's in front of the piece of paper, maybe right about there. Let's say that's P. It's also to the right of the xz plane. It's in front of the paper. It's in front of the yz plane. To the right of the xz plane that's kind of going in slanted. Q is 7, -2, 4. So it's over here to the left more. And with perspective, it may not look like it's higher than P, but maybe I'll draw it right about there. That's Q. 2 distinct points determine a line. Maybe I'll try to draw the line so it's bolder over here, and then it goes, as it goes toward the paper and into the paper, it gets lighter and lighter. That's the line we're trying to describe in these 3 ways. What is the first way? The vector way. Vector description. All these ways, well, the first 2 ways, the vector description and the parametric equations, are functions of a parameter typically called t, typically thought of as being time, though it doesn't have to be time. Our textbook uses a cursive lowercase l as the name for this function of t, L for line. And the line is not the green line. This green line is pointing to the point P. The line is the red line. So the point P is right there. There's a couple different approaches when you got these 2 points. You could first start with the position vector, either from the origin to the point P, or from the origin to the point Q. It doesn't matter which. I'll do the origin to the point P, and maybe write it like this. And somewhat more traditionally in this context, I actually put a full arrow above the letters instead of a half arrow. Kind of to emphasize that these are 2 points. The O is the origin. And the point P, and I'm drawing an arrow connecting these points from the point O to the point P. And then you add t times a vector, call it D, and I'll make that one a half arrow. So this thing is a vector from the origin O to P. Maybe to emphasize it's an O instead of a 0, I might make a little curly Q in here. And D is called a direction vector. Direction vector for the line. A direction vector, it's not unique. And how do you find D? You effectively you can take the arrow connecting P to Q. That arrow right there, which you could write like this. Arrow from P to Q. Like that. What are these vectors? The vector from the origin to P is going to have components equal to the coordinates of P. It's the position vector for P. P sitting up here in space, the origin's down there. Draw an arrow from the origin to that point, its components are going to be the same as the coordinates of P. 2, 1, 5. What about the displacement vector from P to Q? I hope it makes some intuitive sense that you would take the coordinates of Q and subtract the corresponding coordinates of P. If that makes some intuitive sense. So you do 7 minus 2, negative 2 minus 1, and then 4 minus 5. So the components are going to be 5, negative 3, negative 1. Is that right? I'm not proving it. I hope it seems somewhat intuitive. Take the coordinates of Q and subtract the coordinates of P, and you'll get this red arrow. That arrow in this picture is kind of coming out of the screen at you. So its X component should be positive. It is. It is going to the left. So its Y component should be negative. It is. And is it going up or down? That's hard to tell. It depends on how you draw with perspective. It is going up a bit. Q is a bit higher than P is. Second, oh no, actually, sorry, it's going down. It's hard to tell. Q is a bit lower than P is, even though it looks like it's, well, level or something, or no, just not drawn ideally. It's negative. It is going down by a slight amount. Combine these things. L of T is going to be 215 plus T times 5, negative 3, negative 1. That would be the vector description. As T varies, what's going on here is as T varies, you got this fixed vector from the origin to P, this little green arrow that I just drew right there. As T varies, you're taking that vector from the origin to P and adding scalar multiples of this red vector. Positive scalar multiples are going to scale the vector, the red vector, in this direction, giving you points over here. Negative scalar multiples are going to take that vector and turn it around the opposite direction, giving you points over here. That's the intuition. It's essentially the geometric meaning of vector addition. It's what you're using. You can draw parallelograms in here as well. But it's like head to tail vector addition is what's going on. What about the parametric equations description? Well, you could argue that L of T itself is a parametric equations description. It is a parametric curve, just in vector form, with parameter T. But the parametric equations description, all you're doing is you are emphasizing what X, Y, and Z are. Description. Yeah, that's supposed to be the word description. X is going to be, look at the first components, 2 plus 5t. Y is going to be, look at the second components, y minus 3t. Z is going to be the third components, 5 minus t. That's the parametric equations description. You're thinking of it without referring to vectors. But you're seeing the coordinates, x, y, and z, of the points on the red line all depend on the parameter t. You're also asked for the symmetric equations description. This is a little bit odd. We're going to try to understand all this with Mathematica. what you want to do is you want to solve each one of these equations for t. In the first equation, subtract 2 from both sides before dividing both sides by 5. In the second equation, subtract 1 from both sides before dividing both sides by -3. And in the third one, subtract 5 from both sides before dividing both sides by -1. And for the symmetric equations description, since those are all equal to the parameter t, you can set them all equal to each other. X minus 2 over 5 equals y minus 1 over -3 equals z minus 5 over -1. Now, there are other ways of writing this. You could multiply all these equations by 15, for example, to cancel the fractions. Maybe -15 to get rid of the negative sign on that part, at least if you wanted to. You should realize when you look at this, it's really representing 3 equations. It's representing x minus 2 over 5 equals y minus 1 over -3, and x minus 2 over 5 equals z minus 5 over -1, and y minus 1 over -3 equals z minus 5 over -1. All of those are equal to each other, so you can write it as 3 separate equations if you like. Or we just shorthand it like this. All right, what does this mean? What is this telling you? How is it beneficial? Let's use Mathematica to confirm all this and see how to understand, especially the symmetric equations now. So P has coordinates 2, 1, 5. I'll type that in as a list. List in Mathematica can be interpreted either as points or as vectors. It depends on how you're using them. But you use curly braces, you don't use parentheses, and you don't use pointing brackets. Semicolons can suppress output, but I also just like separating the equations with semicolons. 7, -2, 4. So there's P and Q. I can define that direction vector D to be Q minus P effectively, because that's what I did. I took the coordinates of Q and subtracted the corresponding coordinates of P. Yeah, that's our D vector, 5, -3, -1. So there's the vectors. If I want to plot all this in 3 dimensions, probably I need to combine some different things. Parametric plot 3D will graph the curve itself. If I want to plot points, I think the thing to use is called list point plot 3D. I could try drawing some arrows in there as well. Let's try to keep it as minimal as possible to go as fast as possible. Parametric plot 3D. Probably the quickest way to type this is as P plus T times D. That's how I wrote it by hand. Effectively right there. I'm using P in Mathematica because that could be thought of as representing the vector from the origin to P. And this is D. As T varies over some range of values, say -3 to 3 or something, might like to make it colored and pick, say, red. And that'll plot the line there. There it is. We want to plot the points P and Q. I think it's list point plot 3D is one way to plot them. P and Q, there they are. If I'd like to get some perspective on where this is, again, Mathematica makes the positive x-axis go to the right, whereas I made it come toward you more. So I'd have to turn this thing. But I could also maybe do another parametric plot 3D in here to plot the axes. In fact, maybe it'd be best to do this. Axes, parametric plot 3D. I showed you this before. T 0, 0, 0, T 0, 0, 0, T. T going between, oh, I don't know, 10 to negative 10 to 10. And once I've got that in there, it's stored in the variable that I called axes that I can put in here as well. Oops, with a comma. There we go. So there you see it with axes. And again, if I rotate it in a certain way, it'll be more like the perspective that I drew it. If I rotate it around this way. That's more like I drew it right about there. You can get the arrows in there. You can get the vectors in there as well. I won't show you that right now. Might be good to try to figure out what these symmetric equations are showing, though. Can I plot effectively these three separate equations? These three separate linear equations in x and y are all, in fact, going to be planes. To make planes based on those kinds of equations, what you'd want to use is contour plot 3D. Oh, x minus 2 over 5 equals. You got to use double equal signs here when doing this. That'll be one equation, one plane. I got to give ranges of values for all three variables, even though you don't see a z in there. So this is one plane. I might want to make it somewhat see-through plot style. I need contour style, actually, if it's contour plot. Contour style. Opacity makes it somewhat see-through. 5, maybe. So you can see it looks like it's containing both of those points, that entire line, in fact. Can I plot the other equations? I think so. A bit of copying and pasting here. The z expression is z minus 5 over negative 1. It's a second plane. And then the y equation with y and z would be this. So these are the graphing all three symmetric equations. It's giving us three separate planes, but they all intersect on that line. That's what's going on. In general, three planes are not going to intersect on the same line. But if you solve for the symmetric equations correctly, they will intersect on the same line. Other problems include trying to describe, if you've got two lines, determine if the described lines are the same line, parallel lines, intersecting, or skew lines. What does that mean? So the same lines, well, that's the same line. There are different ways of parameterizing the exact same line. One thing you would need for sure is you would need the d vectors to be parallel to each other. Are they? Are they scalar multiples of each other? In 15, it looks like they are. The second one is negative 2 times the first one. If they were not scalar multiples of each other, they could not be the same line. They also could not be parallel. So these two lines are either going to be the same line or they're going to be parallel. But which one is it? Are they the same or are they just parallel but not the same? You can't really tell so easily just by looking at it, because the starting points are just in different spots. And the direction vectors are, they're parallel, but they're not the same. If they have the same symmetric equations, they're going to be the same. Or equivalent symmetric equations, at least, that are scalar multiples of each other. So let's go ahead and see if we can figure that out here for this example. So in the first case, L1, the parametric equations for L1 are x equals 1 plus 2t, y equals 2 minus t, z equals 1 plus t. And for L2, x equals 3 minus 4t, y equals 3 plus 2t, z equals 3 minus 2t. Solving for t, in each of these cases, gives you the symmetric equations. They won't necessarily look the same. The question is, are they effectively scalar multiples of each other or not? The x version, I'd subtract 1 and divide both sides by 2. The t value would be x minus 1 over 2. For the y equation, I would subtract 2 and divide by -1. And for the z equation, I would subtract 1 and divide by 1. For this one, the x equation, I would solve for t by subtracting 3 and dividing by -4. For the y equation, solve for t by subtracting 3 and dividing by 2. And for this one, subtract 3 and divide by -2. And looking at these, well, the bottoms are the -2 times the bottom of the originals. That's because those direction vectors are the same, but the tops are not scalar multiples of each other. Could they be made to be? No. If you can find one point that is on both, they'll be the same if you already know they're parallel. An example of one point that's on this one, very simply, is 1, 2, 1. Right? Set t equal to 0. 1, 2, 1 definitely satisfies these equations. That point makes all these things 0. Does it satisfy these? If I plug in x equals 1, y equals 2, z equals 1, do I get equality here? X equals 1 gives this. I'll put question marks above the equal signs. Is that equal to 2 minus 3 over 2? Is that equal to 1 minus 3 over -2? If any one of these numbers is different, then it's not the same line. This number is 1/2. This number is -1/2, it looks like. And this number is +1. It looks like they're not the same line because those are all 3 different numbers. So I took the coordinates of a point that I knew for sure was on this line, checked to see if these equations are satisfied for the second line. It looks like they're not. If 2 of them were equal and 1 were different, it still would not be the same one.